This video shows virtual labs from Olin College of Engineering's course, Quantitative Engineering Analysis. All materials shown in this video are freely available for use or adaptation. Quantitative Engineering Analysis, or QEA, is an integrated course that teaches foundational math, physics, and engineering content. The course is designed around a series of modules, each of which integrates content from multiple disciplines and culminates in at least one hands-on, real-world engineering project. The materials in this video are from a module called Robo Ninja Warrior, where students learn about multivariable and vector calculus, robotics, and optimization through a series of robotics challenges. For in-person instruction, we use an adapted Nido vacuum cleaner that can be programmed on a student laptop through MATLAB. The robotic platform, as well as all the hardware needed to wirelessly interface with the student laptop, can be purchased for $400. The attractive features of this robot are that it is sturdy, reliable, and has a number of powerful sensors, such as LiDAR. This year, in response to the pandemic, we adapted this module to run using a simulated robot. In this video, I'll show you 4 different simulated environments we use as part of this module. The first challenge in this module is called Crossing the Bridge of Doom. In this challenge, students are given a parametric equation that describes the center line of a wooden bridge. Their task is to get the robot to successfully and autonomously drive the bridge without falling off the sides. This challenge teaches students about vector calculus, robot kinematics, sensors, and calibration. Here, I'm launching the Bridge of Doom simulation from MATLAB using a provided script. Once the simulation is started, we use Docker to spin up the open source libraries ROS for robot communication and programming, and Gazebo for 3D visualizations and physics simulation. By using Docker, a student can set up the software quickly and easily on their computer. Docker also allows these simulations to run on Linux, Windows, or Mac. Next, we'll show you what the result of a student doing the Bridge of Doom challenge would look like. A student would program the robot in MATLAB using ROS's publish and subscribe architecture. Their code would place the robot at the start of the bridge and adjust its wheel velocities to values they computed using their robot kinematics and vector calculus equations. The result is a robot that can successfully travel across the harrowing Bridge of Doom, although this robot in the video got a little overzealous and fell off at the end. The next challenge, Flatland, students learn about the idea of gradient ascent by programming the robot to navigate up the direction of steepest ascent to reach the maximum of a function. Here, we are showing the simulated environment we use for this challenge. The simulated environment projects the function that the students are ascending along with its level curves onto the ground. Students then program their robot to move perpendicular to the level curves to reach the highest point of the function. In this video, we're not showing off a student solution, but instead showing off the teleoperation feature of the simulator, where students can drive their robot around manually. We've also run this challenge in the past, where students program their robot to ascend a physical mountain using an accelerometer to estimate the direction of steepest ascent. In the final challenge, students program their robot to navigate on a course consisting of walls and square obstacles to reach a cylindrical goal. This challenge teaches students about the potential field method of robotic path planning, various approaches to line fitting, and robust optimization using the ransack method. Here, I am showing how the teleoperation script can also visualize the output of the LiDAR sensor, which provides the location of detected objects around the robot. Finally, as an extra bonus, we added a 3D simulation of Olin's dining hall so students could drive around it. We felt like this would provide students with a fun way to connect, if only virtually, with the place they just left a few weeks before. This semester, we are adapting another QEA module called To Float a Boat for online learning. In this module, students learn about multivariable calculus, forces, torques, and statics. The simulated environments we have created teach students about the concepts of center of mass, buoyancy, stable and unstable equilibria, and the creation of boat hulls to meet specific design specifications. At the end of the module, students will 3D print their boat so that they can test it in the kiddie pool. If any of this is interesting to you, we'd love to have a conversation. Everything you saw in this video is freely available to use or adapt. Please drop me a line if you'd like to learn more.